Okay, so now the next chapter we're going to do is talking about making solutions, and an awful lot of chemistry happens in terms of being in solution. Way more than happens in terms of gases, or way more than certainly happens in terms of solids. Most of the stuff we do actually happens in terms of solutions. So what is a solution? You might not remember this from the beginning of the year, but a solution is a homogeneous mixture that's made up of either a solid, a liquid, or gas combined with another solid, liquid, or gas. The solvent is the one that you have the most of. So if you were talking about a mixture where we're talking about air, nitrogen would be the solvent because it's 70-some% of the atmosphere. Whereas if you were talking about salt water, like the ocean, water would be the solvent because you have more water than you do salt. So it's just a matter of what you have the most of. The solute is a chemical that you have the least amount of, so, or a smaller amount of. So for example, salt water, it would be the salt. If you're talking air, the solutes could be carbon dioxide or oxygen or argon, whatever else is floating around in the air. So there's some other examples here. If you're talking about soda, soda's got carbon dioxide dissolved in water. If you're talking about a metal alloy, it'd be stuff like copper and zinc mixing together to make brass. And it's just a matter of which one you have the more of that determines the solute and the solvent. Now, recognize that all of these start with the letters SOL. Okay? It's easy to mix them up. Just be aware of that. So an aqueous solution is the majority of what we're going to be dealing with. That is when water is a solvent. So if I take salt and I dissolve it in water and I get an aqueous solution, that means it dissolves in water and it's floating around in water. Concentrated solutions are something where you have more solute present. We're actually going to do a lab with this where you guys get to make Kool-Aid, and you get to make concentrated Kool-Aid and then dilute Kool-Aid. And so concentrated means it's got more solute present for the same volume of solvent, and dilute means you got less. So like dissolves like is one of the common phrases we use here, and it all depends on those intermolecular attractive forces that we learned about in chapter 12. If something is a polar solvent, and water is very polar, it will dissolve other things that are polar or ionic. So things that are polar would be things like sugar. Ionic would be things like salt. They dissolve very well in water because they have similar intermolecular attractive forces. Ionic is just an extreme version of polar. So alcohol is polar, or maybe even has hydrogen bonding, depending on how big it is. It dissolves in water. Salts dissolve in water. But oil, on the other hand, does not dissolve in water because all it has is LDF. It is a non-polar molecule, and it doesn't dissolve very well in water. So non-polar solvents dissolve non-polar solutes. So this will vary your oil and gasoline. They dissolve very well together because they're both non-polar. Some oils will dissolve in alcohol, but it has to be a pretty big alcohol to make it work. So this is how the solvation process works, not salvation, solvation. You've got your sodium chloride, and it's got a positive charge and a negative charge on the atoms, and then you've got your water molecules. One end of it is negative, one end of it is positive. And when it comes close to the NaCl, what happens is the positive ends of the oxygen line up close to the negative chlorides. And then the negative ends of the water line up close to the sodiums. And they attract each other, and what happens is there's an attraction here, and it pulls the sodium out. Or there's an attraction here, and it pulls the chloride out. So when it comes to solubility, that means how much stuff dissolves in a given amount of water, or a given amount of a substance. So an insoluble salt won't dissolve very much. And there are certainly some like that. A good example of that would be calcium carbonate, which is what coral reefs are made out of. And it doesn't dissolve very well in water. It tends to sit in the ocean for a long time without dissolving. And that's because the calcium and the carbonate are more attracted to each other than they are to the water. It won't dissolve. A soluble salt would be something like NaCl. It is very much attracted. It's more attracted to the water than it is to each other, and so they break apart and they dissolve. So there are several ways to increase the solubility in a liquid solvent. So if you're talking about dissolving something in water, so if you're talking about a solid, one way to do it is heat it up. You may have noticed that sugar dissolves better in hot tea versus cold tea. And another way to do it is create more opportunities for the solid and liquid to interact. So one of the big things you can do with that is increase the surface area. If you're looking at a sugar cube versus powdered sugar, Okay, powdered sugar has a greater surface area and it's going to dissolve better because all the water molecules can get in to all the different little particles compared to a sugar cube where the ones on the inside are just kind of trapped waiting their turn. And then you can stir the mixture. That's the other thing. That's another good thing you can do. If you stir it up, you're going to have them collide with each other more often and they're more likely to interact and dissolve. For a gas, though, gases are the exact opposite of solids when it comes to making the dissolve. If you have a gas dissolved in a liquid solution, it's pretty unstable to begin with. And maintaining the stability is the way to keep it dissolved. So, for example, you've probably all had a soda at some point in your life. And one of the things you want to do is you want to keep it cold. Because if you keep it cold, you're going to lower the kinetic energy, which means it's going to be a little bit more stable and it's more likely to stay dissolved in the water. Hot soda doesn't last very long as fizzy. Avoid agitation. In other words, you don't want to shake it up. Okay, if you've ever dropped a can of soda and then tried to open it, you know what happens. And if you avoid agitation, again, you're going to lower the kinetic energy. You're going to keep it a little bit more stable. And then the last thing is increasing the pressure. So if you've ever opened up a can of soda, the first thing you hear is that little psst noise. Because what's happening is when the soda manufacturers bottle the soda, they store it under increased pressure, which literally pushes the gas into the water. It literally pushes it in there and helps it stay dissolved. When you decrease the pressure on a gas, if you left an open can of soda, even if you left it in the fridge all night, it'll still go flat because it's not under that kind of pressure. So now we're going to talk a little bit about solubility graphs. And so solubility is the amount of solute that will dissolve in a given amount of solvent. Since we're talking about water, it's usually measured with water. A saturated solution is when you get to the point where you stir it up and you shake it and you do everything you can to make that solute dissolve and it just stuffs. It won't dissolve. You have chunks of the solid floating on the bottom. And you do eventually get to that point. Salt, it's a little bit sooner than sugar. Sugar, you can dissolve a lot of sugar in a little bit of water. An unsaturated solution means you dump some salt or you dump some sugar into the water and you stir it up and it dissolves, which means it was unsaturated. If you dump it in there and it sinks to the bottom and you stir it and you stir it and you stir it and nothing happens, then that's saturated. But anything less than that is considered to be unsaturated. And then there's this thing called supersaturated. And in supersaturated, what you do is you kind of trick the solution to dissolving more than it possibly can. And I'll talk about that when we do the demo with this one, because it's really cool. So this is what a solubility graph looks like. So it comes from the New York Regents exam. Miss Ellis probably has this in your reference tables. But anyhow, the idea is, if you notice, on the y-axis, it's talking about the grams of water, and it's talking specifically 100 grams, because remember, solubility is a given amount of solvent. So we're talking 100 grams of water, and on the x-axis is temperature. And then you have all these lines and all these chemicals. And what these lines represent is they represent, at any temperature, so say 90 degrees, the maximum amount of NH4Cl, for example, in this case. So at 90 degrees, the maximum amount of NH4Cl might be 72 grams of NH4Cl in 100 grams of water is saturated. That's the most you can dissolve. Okay? So the line indicates the maximum amount of solute that can be dissolved in 100 grams of water at any temperature. And it shows the amount of solute that would produce what's called a saturated solution. So that's what you're going to use it for. You're going to use this, and anywhere on that line, depending on which chemical it is, it corresponds to the saturated point. If it's below the line, it is considered to be unsaturated. In other words, it's less than the maximum. And if it's above the line for any one chemical, then it's going to be supersaturated because it's beyond the maximum. So, for example, how much KNO3 is needed to make a saturated solution in 100 grams of water? That's kind of like a technical thing to be correct at 40 degrees. So what you do is you find 40 degrees, and you go up on the little graph until you find KNO3, which is way up here at the top. And you're looking for where the line hits 40 degrees. So there's KNO3, it's pointing to this line. And that temperature looks to me to be about that mass is about 65 grams of KNO3. Now there's going to be a little bit of leeway here, okay? You don't have to get exactly 65. If you said 67 or 63, you'd probably be okay. Now if you start saying 69 or 61, probably that's a little bit too far away from where this is positioned at 40 degrees. Okay, so for the next one, you have 50 grams of NH4Cl. Again, 100 grams of water, just kind of being technically correct, 60 degrees. So I'm looking at 60 degrees. I'm going to find NH4Cl. Looks to me like NH4Cl. Right there, that's the line for it. At 60 degrees, it looks like I can dissolve maybe 57 grams. It says it's got 50 grams dissolved. Well, it looks like this is the maximum. And so 57 is the maximum amount you can dissolve. It's only done 50, therefore I would call that unsaturated. So it's just a matter of interpreting the graph and knowing how to use it. Now, here's the tough question. I'm going to erase the ink on here. All right, which ones are gases? Well, all right, if you remember back to when we were talking about ways to increase solubility, for solids, as you increase the top temperature, more will dissolve, generally speaking. For a gas, though, when you increase the temperature, think about keeping a soda warm. Okay, a soda, if it gets warm, it's going to lose those gas particles. They're going to gain kinetic energy, and they're going to evaporate. They're just going to go away. And so if you increase the temperature, less of a gas will dissolve. So what you're looking for here, the ones that are gases are the ones that decrease as temperature goes up. So it looks to me like there's 3 of them that go down as the temperature goes up. So it would be SO2, HCl, and NH3 for the answers for that question. Okay, because they decrease in concentration decrease in solubility as the temperature increases. So we'll do some demos for you and demonstrate what it looks like to see something supersaturated.